Hello and welcome to Engineering Tomorrow. My name is Betsy Fortman, and I am super excited to be able to share this lab with you today. We are going to be talking about biomechanical engineering and how we can use assistive technology and devices to really help enhance a person's life. So let's get started and see what it all entails. You can see in our lab today, we have our main lab, which we'll be focusing on, but we also have a few really interesting extensions that I will walk you through as well if you're interested in learning more. So here we go. As we start learning about different users and people that may have specific diseases that start limiting their range of motion. For example, if someone has like Lou Gehrig's disease or ALS, they may start losing control of their arms, their legs, their speech even. But one thing is really amazing. They have the ability to control their eyes. And as an engineer, how awesome is this? They can communicate with their world, with their loved ones, with their employees, with their employers, with their doctors, all using their eyes. And let's see how this all is made possible. Notice the user is actually using their eyes to backspace as they type. Isn't that incredible? We'll talk more about that as we go.
I look forward to seeing you all at the golf outing.
Wow, what did you notice? Did you notice that it took a little bit of time for our user to get an entire sentence out? Imagine if you had something big to say, something long. So, with our technologies these days, you all have your phones and you know how quickly things are adapting with our technologies, where it can start, understanding what we might be trying to say and actually give us different words to kind of help auto-complete. We're going to talk a little bit more detail about how this happens, as well as how the patient is using their eyes to communicate. Real quickly, before we jump into all of those details, I wanted to share with you our wonderful team that helped to develop this lab. You can see Dixon Cleveland over there on the left, myself, Betsy Fortman, and two wonderful college mentors that helped us create this lab as well, both Allie and Grace. Real quickly, who I am and why I'm here with you today. I am an engineer. I started out from Purdue University where I did something called co-oping, where I got to go to school half the year and I got to work the other half the year. I started my journey with NASA while I was still at Purdue, where I was at NASA Langley Research Center, mainly doing aircraft. But I really had my heart set on space. So when I graduated, I went down to NASA Johnson Space Center, where I worked on all of these different vehicles in one capacity or another, training our astronauts and teaching them the guidance, navigation, and control system, along with all the other ones that go along on board the International Space Station, laying the groundwork for what we know as Orion and the Commercial Crew Program, things like SpaceX and Boeing. And my latest adventure is working with Sophic Synergistics, helping Axiom Space Station with all of their human systems integration. So that's me in a real quick nutshell. Human systems integration is super important because it's having a human interact with hardware and software in order to communicate, just like we're doing in this lab. And so I really am passionate about this topic, and I hope that you'll feel that energy and want to get involved as well. All right, one of the very important things that we need to talk about if we're talking about any kind of eye gaze or any other technology that would help with the user trying to communicate or actually control their environment. You'll notice that we use this term called dwell time. It's how long someone's eye sits on a given command, whether that be a letter or a command to move. It's all the same. How long does their eye hold that button in order for the computer to register it? So I want you to think about that dwell time and remember how our patient in that previous video was using his eyes to communicate, I can't wait to see you at the golf outing. And he actually backspaced, remember? So the computer has to know when someone's eyes are like going from one place to another, but also has to be able to backspace and say, no, that wasn't the command you thought. This is what I need to say. So with that dwell time in mind, I have a quick activity for you. Are you ready? Here we go. I would like you to get ready to type with your eyes in order to say, how are you doing today? I'm going to set my timer at 15 seconds, and I would like you to think how long you have to rest your eye on a given button to say this. Are you ready? Here we go. Go. Raise your hand if you got it. All right. How many of you were able to get that entire sentence out with your eyes? Raise your hands. If you are one of those, awesome job. If you didn't get there, I totally understand. It takes a while for our eyes to get to a given character and to hold our gaze there long enough for the computer to take it. And today we're going to talk about just like that length of time that it takes, what technologies we have today, and which ones hopefully you guys will be a part of as you become future engineers, possibly to help solve these problems and make things more and more functional for our users. So let's jump right in. One of the things that you may hear about, so not only is a user trying to talk, but they also may need to interact with their environment, right? If you wanted to turn the lights out because it's time to go to sleep, you would want to be able to control that. You might want to be able to control how hot or cold your room is, and all of those things, answering a phone, and all of that. So you can see here, the Internet of Things is how we kind of tie all these things together. And one of the templates that you could be making as an engineer is this control panel so that a person can bring up different menus to control all those areas of their life. So amazing. So as an engineer, we need to think about A, what movements do our, users need? What ones do they have that are available to them? And then how can we help kind of bridge that gap with the things that they can do well? In our case, they can move their eyes very well and very accurately. And so we're going to take advantage of that and really hone in on like how we can use that to communicate. All right, so you might be wondering, okay, like when did this all start, right? Well, back in the 1870s was the very first recording of, someone understanding fixations and cicadas. Now that means like what someone's looking at is a fixation, and cicadas are like how quickly someone's eyes can track something left to right, up and down, in the different movements that they might be doing with their eyes. So that was back in the 1870s. Can you believe that? Crazy, right? Well, as we start kind of going forward, one of the other major things that starts happening in the 1930s, this is when we start getting like those old picture movies, right? And what's so cool is in the 1930s, kind of in parallel, then they could use this technology. And all of a sudden, we start having the first recordings of actual eye movements. As our technology advances further, another highlight I want to point out is the computer developments. So, like in the 1980s, you'll see here, there is this emergence of eye tracking in real time. So, computers can then start understanding and looping in real time what is happening. The 1990s, this progresses with the first use of eye tracking within the field. And then today, things are evolving so fast. If you think about typing something on your phone and how if you're typing the word dog, D-O, it will probably give you a list at the top of words that start with those letters so that you can quickly get to what you're trying to say. And the same is true with these eye tracking developments. They're just increasing every day. You can be a part of that. Let's lay out the terminology so that we'll be able to use it to our advantage. We have our user, and where they are looking is called the gaze point. So, like wherever we're looking, that's a pretty easy one, right? We have our gaze line here, our eye location. How this all works together. This is so cool. It's just like your phone. I think of it a lot like that. Instead of the camera being at the top, it's at the bottom. And if you've ever done like a video recording, you know that there's this light that shines as you're recording to kind of light things up. Same is true here. Again, not on the top, but it's coming from the bottom right next to that camera. And when we shine that light, it will reflect in the cornea of an eye. And that reflection is how we're going to do all of our cool geometry to start helping us and our patients. So let's take a look at the eye. Here we have our eye. The very center of it we call the pupil. And when we move our eye, we will notice that, that orientation is going to move around. What's going to be so important is where that reflection, remember I said there's going to be this light, there's going to be a reflection of our cornea. And we're going to look at that compared to the center of our eye or the center of the pupil to know how far we've shifted our eyes. And let me give you a quick demonstration of what I'm talking about here. So here is our eye. I'm turning off the light so you can kind of see the light a little closer. All right. Now, as I have my camera and my light, I have a given vector. We call this the glint vector, one where that reflection is to the pupil. Now, as I look up, notice that vector has gotten a lot bigger, right? It went from here all the way up now. And if I come back, it's smaller. Guess what? Similarly, we could have it if I'm looking left or right. That vector then changes depending on how I am looking. I'll give you a quick background of what the computer does with this, and then you get to draw your own. So let's go. The very first thing that happens is our user has the light reflecting and an image is taken. So just like you saw with my giant eye, doop, there is a light. That reflection, and then the computer itself will go and find the center of the pupil. In our case, it's this red cross. The next thing the computer has to say is, where is the center of this light? It will make another cross mark. In this case, for ours, is a green one. So there's a red one and a green one. And now the computer in its algorithm will calculate what that pupil glint factor is. Once it knows this, it has a whole bunch of these stored up inside the computer brain, basically. So it has all these stored, these images of which vector it should be. And then it goes through and compares which vector matches the one that I just snapped a picture of. And then by that, it says, okay, this one looks like it. This is my command. It's either an A or a B or a stop or a go. Whatever is tied to that location on the screen is the command that is sent. Isn't that cool? So that's kind of the algorithm going on behind it. Again, what you're going to notice if the eye moves up, there's a vector. We call this, when we go up and down, is called the offset. And when we go left and right, we call that angle the heading angle. We can break down any way we're looking into two components, two vectors, one that goes up and one that goes left, or one that goes up and one that goes right, or one that goes down. And notice that when we add these vectors together, you will get this resulting vector. And we do have an extension where you get to work calculating those angles. What is the offset angle? If I know how far up that glint vector is, or how far over someone is looking with that heading angle, and you get to calculate those as well. In your workbook, you will notice, so not only will you have the physical model that you'll be working with, there's actually one online as well. If you click the link in your workbook, it will bring you up to GeoGebra. I love this model because it gives you that 3D representation of the eye. Let me just show you how it works so that you'll be able to do this really easily. If you hold your right button and you can drag around which view you're looking at, and so that's kind of helpful if you want to look at the eye from different ways. The red line down here shows you where the camera is. where that computer, and the light and all of that stuff are. And then here's our pupil. And this is the part you get to do. You get to pull the pupil like you're moving your eye around. As you do that, you can see how that geometry is changing. What's really cool is we're going to look at two different ways. One, when we're looking with the camera on to the right, so like we're kind of looking straight into it. And then another when you're looking face on, like we can see the eye and we can see, oh, it went that far. So we're going to take a look at both of those ways of our eye moving and how those vectors all end up giving us the vector from the pupil to the glint spot. And that is all that you need in order to be able to do these yourselves. Isn't that amazing? You guys have enough math to help so many people in this world. It is incredible. All right, so we've talked about how it has all these vectors stored in the brain of the computer, right? And those vectors correspond to certain points on the screen, which is where we would want to put our buttons or our commands and all of those good things. If we have 100 different vectors, then we could have 100 different points. So however many different commands you want to send are however many that the computer will need to know inside its memory. All right, so I've alluded to it. Go ahead and take out your eyes, or you could be doing this after the fact, after watching this. And you will then hold the eye opposite you as if you are the computer yourself and your flashlights. As you have already painted or put on with your Sharpie your pupil, now rotate the eye and notice how far away that light that you're holding, which you're not moving, hopefully, is changing. If you notice from where that pupil is, as you're moving it left and right, up and down, and all kinds of different ways that the eye might move, you'll notice that that distance is changing based on how you changed that eye location. Once you have this, you're going to make in your workbook a drawing of one of the locations as you've moved your eye around. In your case, you will be holding an ornament. Again, that like just hold the side that has that little clasp. It's the easiest way to kind of hang on to it. And here are your materials that you'll be using. Um, I recommend that you try to hold as still as possible. Maybe one of you is holding it and the other is kind of in line and drawing it. Or if you can, you may even want to take and have someone snap a photo of it to include in your workbook as well. All right, so that's activity number one. It's really just a demonstration of like how the eye works and how this geometry is happening kind of behind the scenes in the computer in order to determine what we're trying to do and where we're trying to go or say. So, activity number two, you can see on the screen that we have a user who is trying to maneuver their wheelchair. So imagine that you would like to go from your bedroom out to have dinner with your family in the kitchen. Maybe you can't eat, but just being able to be near your loved ones as they're having something like dinner or any other conversation. You want to be able to get there and be with them, right? So let's take a look at how we can do that. There is a company called LifeDrive, and it's founded by one of our AT engineers, John Sexton. You can kind of see over here. And he was inspired because his dad was going through this disease, and he wanted to be able to help his father become more and more independent. And so he has worked some of this technology that we're talking about and helped to create the ability for the wheelchair to move. So let's try to imagine that we're the computer right now. We have all these vectors stored in our brain. Here are three of them that are stored in our brain. Now, you take a snapshot, and all of a sudden, you see that you have this pupil glint vector. All right, now you're the computer. What are you going to do with that? Do you think the person is looking at location number one, two, or three on the computer? Let me know your thought. All right. If you guys guess number three, you are correct. So if the computer compares and says, oh, this is my command, I need to Stop. Very good. So this might have been your wheelchair is moving and you've just looked to the command to say stop. Very nice job. All right, here's another one. We'll go through this one a little faster for you. All right, which way should we move our wheelchair? Awesome. You said right. Very good. All right, next movement. Good. Forward. Next one. Right again. And lastly, left. Very good. So you have just traveled through your house in order to join your family. Isn't that incredible? You went right, straight, right, left. Very nice. High five to all of you out there. All right, we are going to make our own templates in order to do this. So let's jump right to your supplies. You should have a couple of sheets. You get to create your own template using your see-through sheets. I think we've included some page protectors for you and some dry erase markers. We want to make sure we're not using Sharpie. That way, when you use your dry erase, you'll be able to change up your templates and make different ones if you find that you need to make some refinements. And then lastly, we have given you some floor plans. I'll explain those in a little more detail in a second, but what you'll know is that you're trying to get from point A to point B. This might be a user trying to get from one part of the hospital to the doctor's office. It could be anything. So keep that in mind as you are envisioning these mazes to be your floor plans of where you're going. All right, here's your setup. You will create a template. Now, your template could be almost anything. I'm going to let that up to you. Um, the easiest template you could make is probably one that looks like this. Up, down, left, or right. But that doesn't give you a whole lot of like refinements. So think about that. How many different directions might you want to include? You'll have your user. So this would be your person who is trying to move the wheelchair. Your engineer is going to be the computer. This is the person looking at the person's eye movements and translating them into the movements of the chair. They will be drawing which way the chair should move. Okay. Then you have your observers. So you could have one or two, depending on the number of people in your particular group. One will be recording like how many steps they have gone correctly and incorrectly. And we will be doing some calculations. So let's take a look here specifically at our distances. Now, in this example, it's suggesting that you go 12 inches and 12 inches. Whatever you choose, whether it's 12 or 10, just keep it constant so that when you're doing your iterations and making changes to your template, that at least something is staying constant so you know what's making the improvements or not improvements. Right, here is an example of the engineer, the person reading the eye movements and deciding which way the chair should go. Here is our user. So our wheelchair user is trying to go from one place to another. And here is our recorder and observer. Notice we had another person here holding up the maze. So we don't want our engineer to know already which way to go, right? We're trying to figure out if they can understand the eye movement commands the best. And so we have it behind their head, but however you choose to do that is totally up to you. Here are a couple examples of how you might hold up the template between the engineer and the user. One, this is through the doorway with a hanger hanging, and this is just a document camera. I may not recommend this one as much because you would have to have people on both sides, but really, you guys be creative. If you want to hold it, if you want to hang it, whatever works best for you, you'll figure it out as you go, I think. We've included several different types of mazes. We have easy, medium, hard, and expert levels. I recommend that in your first couple runs, as you're getting used to everyone's roles and who's doing what, that you start easy. Because as you do this, you're going to start changing your templates a little bit and finding different ways to communicate, like how many movements you want to go forward, how many movements you want to go left. You could do this by adding numbers or doing it with a timing of how long the dwell time is on a given command, totally up to you. We're leaving that as a part of your design that you get to do. So the question would be is, do you want to use one of these or maybe you make your own completely and find out what works best for you. As you are recording, um, you will be putting in here how many moves you had to start, and then how many you got correct. That's going to give your accuracy. When you stick it into these calculations here, you'll notice if you had 9 out of 10 moves correct, you got a 90%. That's awesome, right? In the right-hand column, you are welcome to type the kind of maze that you had, the kind of setup and template, or what I would prefer, if it were me, I would probably just screenshot what my template looked like and then drop it directly into your workbook. So that is the major activity for this particular lab. I'm going to show you real quickly here. In the different floor plans and mazes, you'll notice that we've kind of broken out the steps to help you count how many correct or incorrect moves someone has made. So I would recommend using those with the steps just to kind of help figure out which way you're going and how many you get correct. So I just wanted to show those to you real quick. On the screen, if you like learning about these things, there are several other different assistive technologies out there. I'm going to highlight just a few. AI. Someone starts having these kinds of diseases where they know they're going to lose their voice. AI can record them speaking so that whenever it comes time to have to type out their words, the AI will know how to generate every word a person may ever say, and they can never lose their voice. Isn't that so cool and just so empowering? On the right, you can see there are other devices where now, like gas pedals and brake pedals, can be controlled by buttons if someone maybe doesn't have the use of their legs, but they have the ability to use their other arms and other limbs and things like that. Also, if you're looking at eyes specifically, there are eye tracking glasses that can help ensure where someone is looking. These have applications across the board. You can imagine like insurance companies and things like that would want to know if there is a distracted driver out there and all of those good things. In the middle, this one's near and dear to my heart. This is showing you like someone reading. And they can use this to help identify if someone has an eye tracking problem or if maybe they need to be evaluated for dyslexia or something to that effect. Anyways, I hope you've enjoyed this lab and I can't wait to hear how your designs go. Thank you so much from behalf of Engineering Tomorrow. It's been wonderful being here with you. Now, if you have stayed to the end, I am here to talk about our extensions that we have that associated with this particular lab. So I'm glad that you're here and back again. You'll notice the first extension is what we call an E-tran board. So instead of just trying to control left, right, up and down, straight, and all of those good things, if you wanted to create a template that could help someone speak, maybe you want to have certain commands that they're going to be saying all the time, or maybe you're looking for whole sentences. This is the extension for you. So you will have similar materials. You'll notice you have, again, your page protectors. You might call them acrylic sheets. Either one's fine. And you'll be using some expo markers. This will just help you figure out like what you want to write and where you want to write it in your template. You will see on the left, this is a version. Let's say someone's going to say yes or no almost 10 times a day or something to that effect. If they say something a lot, you could add this to like a main window. Uh, if you're asking them questions where, you might need them to tell you if they need medicine or if they've taken medicine, having the ability to quickly answer it could be very helpful. So having one of your E-tran boards looking like this might be the way to go. All right. And on the right-hand side, so if you want to get into something more complicated, like putting out a whole sentence or a whole paragraph, you need more letters and more words. And so how you want to structure that is totally up to you. These are just some examples. Some people lay them out like your keyboard, like you're used to seeing. Some will place the more frequent letters at the top. Some will space them out and put words and letters. So you might want to do a combination of the left and the rights together in order to have some high frequency words, but also to be able to say bigger, longer sentences that aren't canned responses. So think about that. Very similar to what you've just done. You'll have the setup where someone is trying to say something. Another person is counting how many times they've gotten the correct letters until the entire sentence is spoken. And then you will count the number of times you get it correct and incorrect, and then calculate your accuracy as well. I hope you enjoy that particular extension. Now, if you are interested in geometry, I have two more excellent extensions coming your way. So the first one is our 3D foam model. This is you take that geometry. Remember how we were talking about these vectors? You take that geometry and you decompose it. And so let's look at what we've got here. So we have some foam balls. And you're really trying to figure out exactly if someone's looking up, where are these vectors? Here's the vector to my camera, and then here's the vector that I'm looking. And so being able to model those with some pipe cleaners can really help understand just how intricate this geometry can be. You'll notice here that we've included a small ball to kind of represent the camera and the light that's happening that gets reflected in the eye, and then the major bigger balls to be the eye itself. Uh, there are two different ways you can do this. So you can do the 3D ball to represent your eye, as well as all of these different uh, vectors that you'll be adding, and then the angles that go from one vector to another. Again, we're looking for that offset angle, that how far up or down I'm looking, and how far left or right, that heading angle, and really labeling those with a specific color on your pipe cleaners. And here's that second geometry extension. So look at here at eye geometry calculations. So here's where we get into the really awesome stuff that's going on in the computer. You'll notice here that we're looking at the eye in two different ways. And this is what I was saying when you're making those foam balls, that you'll look at it like head on and then to the side. So here we have our computer and that light. And here we have the pupils, so where someone's looking up or up and over. And you'll notice when we take these two snapshots, one on from the side and one from head on, that we have these right angle triangles. This is awesome. I don't know about you guys, but I love right triangles because there are two super awesome things. Number one, there's the Pythagorean theorem. You might be like having that rush back to your memory. It's where the two small sides we label as A and B, and then the hypotenuse, the long side we call C. And we can use the equation called A squared plus B squared equals C squared. This is awesome for us because then everything we know, we can then calculate anything else. And I love that. Let me go back one. The hypotenuse in this particular one happens to be the radius of the eye. That's pretty awesome, right? So we're going to know the radius. We have that hypotenuse and we can calculate the other ones. Here are a couple other relations that I want to bring to your mind as well. That big long name, SOHCAHTOA. So sine being opposite over hypotenuse, cosine being adjacent over hypotenuse, and tangent opposite over hypotenuse. We can use these to calculate that offset angle. Awesome, awesome. All right, so here's how we do it. I know it looks like it's a lot. Don't worry. It's like one of those plug and chugs that you stick the information in your calculator and you get the answer. And if you're worried or wondering if your calculator has this, there is a free calculator online that is one of my absolute favorites. It is called Desmos Scientific Calculator, and you can get it on any web browser. So you are welcome to use that as well. All right, so here we go. Let's find the glint vector. And that's that vector going from that reflective spot over to our pupil middle. So again, if the person is looking both up and over, this is our compound vector, right? They went up and over. And we could just rotate the eye straight there. Like if you don't usually move our eyes one way than the other, but they sum to give you that composite vector of being both those. All right, here we go. If you have a person and you know their radius is 7, notice everything here is color coded to kind of help you when you go back to do this in your workbook. So we have 7 is our radius, and we know looking at the person that they had this offset or not offset, the heading angle that has this change in distance of 3 millimeters here and a change in up down in the offset of 4. What's really cool here is this 4 is the same as this 4, right? Isn't that amazing? So now we have this triangle has a 7 and a 4, and this triangle over here has a 3 and a 4. We've got like 2 pieces of a 3-piece puzzle on both sides. That is amazing. So we can just work our math, right? Work our magic in the background. So in this particular case, if we're looking at straight head on, we want to know what is that left, right, or what we call the heading angle. This heading angle is defined as A in this particular, between these vectors right here. And you can see we have 4 and 3. 4 being up, 3 being over. And we use a squared plus b squared to get the magnitude of that hypotenuse. And for us, that's super because it goes 3 squared plus 4 squared equals 25. And c is then, boom, 5. So we have all 3 sides. That can really help us because now that we have all 3 sides, we can choose anything we want to figure out A. We can choose the opposite over the hypotenuse. You want to do that one? Let's try that one. Opposite over hypotenuse. We're going to go with the sign of A, and then we put 3 over 5. And then we take the inverse sign and we get our angle is 37 degrees. And guess what, you guys? All of these opened up to be the same because if we use the cosine or the tangent, it would have all gave us the same answer. So whichever way you chose to do it is gonna be right. Isn't that amazing? Okay, so let's jump ahead, assuming we've calculated all of them to be 37 degrees. Next, we want to know, like, okay, now I know they went 37 degrees this way, but how far up? What's that offset angle? Here's our calculations. Again, we're color coded. It's the same problem. We're just looking at it from the other triangle, right? From the side. All right, we have that offset distance of 4. And we remember the cornea, that radius was 7. So if you have these 2 sides, we have the opposite over the hypotenuse. What are you thinking? I agree. I'd probably use the sine. Yeah, just like we did in the last one. Sine of B equals 4 over 7. And again, we work our magic, and the inverse sine of 4 over 7 ends up being 34.85. So we could say they were looking up approximately 35 degrees and over 37. And that's where their eye ended. And now we have where the vector should be pointing. And with all of that magic, you would be able then to compare the vector to the one you got to the ones stored in the computer brain and figure out which spot was my person looking at to send that word, that command, that sentence, that movement of their wheelchair. Just incredible. Anyhow, I hope you've enjoyed this lab and all the extensions. It's been an honor to be here with you today, and I hope you guys enjoy this and share. Please share all your designs. We would love to see what you have and showcase you on our social media. See you soon.